deals with right triangles, and I would be surprised if you haven't seen something about this in the past. So we're dealing with right triangles. Here's how we get away with not writing the word triangle every time that we need to. Right triangles have one 90-degree angle. This is angle. Now we're starting to step into the realm of geometry, which is maybe a good news for some of us. This chapter 5 is the last, or module 5 is the last that we have of algebra for a little while anyway. Okay? So we're kind of starting to head into this new module 6 stuff. I doubt seriously if this is going to be on the test, but it could be. But it's definitely on the assignment. So when we see right triangles, we always have a right angle, and this means 90-degree, I want to write percent there, it's not percent, 90-degree or right angle. If you see something drawn that doesn't look like a 90-degree angle, but it has this little box in it, guess what? It's 90 degrees. Right, forget how it looks. It's what does this little guy say here. So this is also going to be a 90-degree angle. Okay, the box tells us that we're dealing with 90 degrees. Okay? Right, so what? Well, about 2,500 years ago, there was a fellow named Pythagoras. And he was messing around with math. He was a pretty smart fellow. And he happened to notice something when he was goofing with right triangles one day. Specifically, a triangle that had a length of 3, a length of 4, and a length of 5. And what he noticed was this, that if he built a box, a square specifically, off of each side, it looks more like a rectangle than a square. He noticed something special. If he looked at the area of the box that was built off the small leg, so this area would be 3 times 3, or 9 units squared, right? 3 by 3. And then he looked at the area of the medium side, 4 times 4, gave him 16 units squared, whatever the units were. And the area of the big box, 5 times 5, gave him 25 units squared. So he did this, and he noticed that if he added the areas up of the 2 small boxes, that it gave him the area of the big box. Okay? So 25 equals 25. And he did this for many, many right triangles. Now, there's an infinite number of right triangles. There's no way that he could do it for all possible right triangles. But he did it for enough that he came up with a theorem where he said, if I square the length of the 2 small sides and add them together, A and B, I get the length of the third side, the longest side. Oops, sorry, let me get that up here a little bit. A and B are the lengths of the 2 short legs. And it doesn't matter which one you call A and which one you call B. The C is the long leg of the triangle. Does anybody know what we call the long leg of a triangle? Starts with an H. Hypotenuse. Yeah, it's hypotenuse. Now, a word like hypotenuse is loads of fun to say, but it's not all that fun to write over and over again, right? So we're just going to say HYP. We'll shorten it to HYP. Hype, the hypotenuse. Now, why is it a theorem and not a law? Hey, I'm teaching something up here. If you have something to talk about, you can go discuss it in the office, perhaps. Okay. All right, you're good. Okay. Then let's discuss stuff later, like after school. Okay. A theorem is something that we've tested over and over and over again, and it's been true every time we've tested it, for every right triangle we've ever tested. But is it possible to test an infinity of right triangles? No, right? There's no way to test an infinite number of right triangles. So even though it's worked every time, a theorem indicates that the situation is such that there's no way that we can test all of them. Evan? No, that's not a theorem. That's the calculator telling you to go jump in the lake. Okay? All right. I mean, just ask any dinosaur you can run across. They'll tell you that dividing by 0 will, bring Armageddon. It's a bad deal. All right, another thing that we need to know about triangles, right triangles specifically. When we have a right triangle, the hypotenuse is always in the same spot. It's always across from the right angle. The hypotenuse, HYP, is always, we say instead of across, we say opposite. The right angle. It is always opposite the right angle. And you cannot have more than one right angle in a triangle. It doesn't work to have more than one. The hypotenuse, it turns out, is always across from the largest angle, but not all triangles have a hypotenuse. Okay, so example. Given triangle, side lengths, or leg lengths, 9, 40, and 41. Is this a right triangle? That's the question we want to answer. So we take the two short sides. These are our short legs. We're going to call them A and B. And we square them. So we take 9 squared plus 40 squared. And we want to know, this is the hypotenuse, we want to know if those two short legs squared equals the hypotenuse squared. Now, it might be kind of handy to have a calculator for this, but I bet some of them 9 squared? How much is 9 squared? 81, right? So this is 81. How about 40 squared? 1600, right? 4 times 4 is 16, plus a couple of zeros. Now, 41 squared, I don't know. I'm going to give that a look. That is 1681. And 1600 plus 81 is 1681, so it's true. So we would say that this is, or they could be legs of a right triangle. So we'll say yes, right triangle. Pythagoras' theorem works. There's certainly more to talk about on that, but for now I think that's enough. This is the kind of problem you're going to be looking at today. There's, I don't know, 6 or 8 of them. In fact, this is problem number 1 today. Okay. All right. Unfortunately, that's not it. I've got one other thing that's pretty important to give you some notes on today. It's called something called substitutions. Is everybody with me here? Okay. Substitution. You guys know about substitution. It's like when the teacher's sick and some poor sap comes in and you pick on them all day long, right? That's substitution. Right? I don't like subs. They can never be as good as me, so I try to avoid it. But we're going to use substitution to solve systems of equations. Now, I probably need to define systems of equations here for a minute. We've already been working with them, we just haven't called it that yet. When I have a system of equations, what that means is we have 2 linear equations, and we want to know if they have any common solutions. So we have 2 linear equations. And if you haven't noticed, we've been dealing with linear equations since like last September, maybe even August, in one way or another. And we want to know if they have a common solution. Or possibly solutions. That can happen too. So this is combining 2 lines on the same graph. What can happen when we combine 2 lines on the same graph? Well, what I could have is, do I have another color here? Yeah, I got a couple colors. Let's say I have one line on the graph that does like this, and the other line does like this. How many common solutions do these 2 lines have? 1, right. Where the 2 lines cross, we would say this is one solution. And it's going to be in the form of some value of x and some value of y to define that point. Can anybody think of another way that 2 lines could interact with one another that might be a little different than that? What's that? Well, they could, but wouldn't that be that they'd still just cross in one point, perhaps? Yeah. They can. Yeah, they can be the same line. So, and sometimes it's hard to tell. You can't tell by the equation itself if we get tricky, if we math teachers get tricky and write them in a certain way. What we might find is that we are actually looking at two equations that are the same line. How many solutions would we have there? Infinite. They're all of them, right? So this is an infinite number of solutions. Right, that's the third situation. So if it's the same line, we have infinite number of solutions. If we have two lines that never cross, I think I need to get rid of this red pen. This would be no solution, or no solutions. And we'll see situations where these come up. We've actually seen them before, but I don't know that we would have necessarily connected it to a graphing idea. Now, this thing here, these are parallel. And I have to tell you about one of my teachers when I was a kid in seventh grade. I had this geometry class, and it probably was pretty low-level geometry, because I was a pretty low-level kid at that time. Mr. Hollenbaugh, I swear, was 95 years old then. Now I think he's about 150, okay? I actually heard a little while ago that he was still kicking, and I don't know. But this guy was old when I had him as a 7th grader, and it's been a while since I've been in 7th grade. Yeah, probably. So anyway, I had Mr. Hollenbaugh, and he said something that I'll never forget. He told me I'd never forget it too, but I really won't forget it because of the way he said it. He said, "Parallel lines are like railroad tracks. They never cross, and you'll never forget it." And that's exactly how he said it, and God bless him, I never forgot it. Now, what I really remember about Mr. Hollenbaugh was he had no clue. He was not with it at all as a teacher. So we didn't have these fancy things where I could like face you and talk to you. He was writing on the chalkboard. I think it was probably a chalkboard back then. And he's writing his geometry stuff. And there were some students in the class that I was in that had some sort of mechanism that I won't describe that gave them the ability to fling projectiles, shall we say, okay? And he'd be writing back to us, and something would hit the board and make a loud noise, or maybe the trash can. When they hit the trash can, it really made some sound. And he'd kind of jump, and he'd look around, didn't see anything, keep going. I always felt bad for him, but I never felt bad enough to go like tell anybody. So I was never the one to do the projectile, I swear. Okay, but it happened a lot, poor guy. So I will know that I'm too old to teach when I hear projectiles hitting things around me, and yeah, that'll be the last day. I'll know that I'm done. Okay, example. So you have like 6 problems or 6 or 8 problems like this. In fact, this is problem number 1. We have y equals x plus 1. So there's one linear equation. And another linear equation, x plus 2y equals 8. Now the good thing is these are fairly easy problems in terms of substitution because there's not all that much that we have to do. It's going to look kind of long, but it can get worse for what it's worth. I have 4 variables, y, x, and y, right? I need one of them to be solved, or I need to solve for one of them. But in this case, I already have one solved. This y, we know what y equals. It equals x plus 1, right? So what I can do is I can take this x plus 1 and I can replace it. I can substitute it. Becomes like a substitute teacher for this y here. And that's a good thing because then I can say x plus 2 times x plus 1. So I'm replacing the y with an equivalent. And now I have an equation where I just have x's. And if I just have x's, then I can solve it. Okay? So I'm going to distribute the 2 So I'm going to say x plus 2x plus 2 equals 8. And then if it were me, I'd put these two guys together. X plus 2x are on the same side of the equation, so I just add them together. That's 3x plus 2 equals 8. Is everybody with me so far? Now I would subtract 2 from each side. So that's going to cancel this, and I get 3x equals 6, and I bet you guys can tell me what x equals. X equals 2, right. Just divide both sides by 3, and we get that 2. Now, I know what an x is. But coming back here, remember I have x's and y's. So I'm looking for a situation probably where the two lines cross. So I need to know what y is. So I take this value and I do one more substitution. I can take this x and I can put it in either here or here, whichever one I like. It doesn't matter. I'm going to put it in the easy one, which would be this one. Okay? So I'm going to substitute this value here. So that's going to be y equals 2 plus 1, or y equals 3, right? So I know now where these two lines cross. They cross at the point 2, 3. This is my solution to the system of equations. So I don't need to graph it. I just have to do a little bit of algebra. There's many ways to find this. One of them is graphing. Substitution is another option, and there's a third option that we'll learn a little later on. Okay? All right. So that's it for notes.